This is part 6 of the KLEP ecosystem, a symbolic AI that's trying to mimic human cognition, meaning that it makes choices in a way that you make choices. It's how I think that you think, I think. So, this is the key manager, and we're finishing up talking about keys. That's awesome. The key loader was responsible for governing many keys and their dynamic properties. It could return the KCD, the key creation data, with a function call, and this is kind of like the star stuff that makes up keys. So the key manager takes the star stuff, the key stuff, and populates our KLEP key with it, issues it to the neuron, and updates keys if need be. So where the key loader was making the fundamentals of keys, this is actually creating the key, issuing the key, managing the key, which is weird that would be called key manager and it manages keys. So let's begin. The key lifecycle should be understood first. If we go back to the neuron, we can see that in its update cycle, after it has checked for new knowledges, it calls the key manager to tell it to release all the keys that it has in its buffer. The key manager does so. This lets the neuron agents make informed decisions for that frame in regards to what executables are valid and can fire. Then, after it's dealt with all of its executable stuff, it then clears its held keys to remove all that data, where it will be populated again in the next frame. This means that we have two lists of keys to deal with: the currently held keys of the neuron and those that are pushed to the buffer for the next frame. This also means that if we push a key to the buffer, that it's considered for the next frame, whereas if we push a key to the neuron, it's considered in frame. So why not deal with keys in frame only? You can, but its purpose is to trade speed for data purity. If you say have a key that gets pushed to the buffer, then you have an entire frame to change and update that key's data. If you push the key to the neuron, you don't have that, which makes sense, right? But you can encounter situations where it validates multiple executables, which modify that key's data, but they behave in unexpected ways because the key's data is considered before all executables that modify it do so. That's a weird sentence, so let's unpack that with an example, right? So executable 1 pushes data to key 1, like an int or something, for executable 2 to use in a switch. But executable 3 modifies that data again. So executable 2 had already fired, it's not going to fire again. So therefore, it never takes into consideration executable 3's modification. By pushing to the neuron itself, you trade data purity for speed. By waiting a frame, you trade speed for data purity. So that is the difference between pushing to the buffer and pushing to the neuron directly. And that is why we have these two lists. If we take a quick look at the function that issues the buffered keys, we see that it's a simple loop that sends each key in the buffer to the neuron's add key function. Then it clears the buffer, getting ready for any and all keys that get pushed to it for this frame. The neuron is responsible for its stuff, so it should be the one that deals with the held key list, and we try to do that as much as possible, while the key manager is responsible for the buffer stuff. So it should be the one that deals with the buffer list. Is simple, is fun. At the opposite end of this is the cleanup. As we have already mentioned it, let's take a look at that function. And first we do a quick loop looking through all the keys that are immune to the key lifecycle, meaning that they stick around until being told explicitly to leave. Just like me at a party. Because they never get cleaned up, we have to manage them a little bit differently by flipping our bool is in use. This bool is primarily used in debugging, but it could be used for a lot more. And the takeaway here is that you have one of these immortal keys that stick around. This is where you would manage anything that needs to be flipped back at the end of the frame. If you remember from our prior videos, the get property allows for a string to be passed with it, and in this case we are passing the function's name that's calling it, and again this is for debugging reasons. After that, we collect all keys that are not immune to the key lifecycle to be processed. When we have them, we move through each of them, telling the neuron to clean them out of the held elements, get out of there. We reset the properties by cleaning them, and then we add them to our key pool. That's two interesting things that I just said: resetting the properties and using a pool of keys. So let's look at the resetting of properties, as it is super easy. The function cleans the key's properties and assigns it a temporary name, in this case default key, and that's it. Now, pooling keys is more complex, but very nice to have, as it's an optimization technique, and therefore not really needed, but it's nice to have. We could go through and destroy all of these keys, and then next turn make them again, and destroy them, next frame make them again, destroy them. But if we look at the very top, we'll see that we have a key pool and a pool index value. This is where our cleared out, cleaned keys live, and our index keeps track of how many keys we have in the system. As keys are scriptable objects, we have to treat them as objects, and so they need to be managed as objects. Object pools are used in first-person shooters a lot because constantly creating and destroying an object gets computationally expensive. So every time that you start firing your machine gun and it spawns in bullets to take care of like bullet physics and stuff, it's not making a new bullet. It's grabbing from that bullet pool and then putting it in front of your muzzle and then giving it the data to send it forward. This solution is making a bunch of objects, cycling through them. That's the same thing that we're doing here. Before we get into how we're actually doing that, we need to look at our initialization trigger function, and this is called when the neuron sets everything up to start. That object pooling will come out of these triggers. This calls into /bridge to use our universal event system and registers two events and passes our two functions. So whenever these events are called, then these functions will fire. One pushes to the neuron, the other pushes to the buffer. Both are very similar in approach. So let's look at the push to neuron, as I feel it's the most straightforward. When the event is raised, we check to see if the data being passed to that function is a KCD, key creation data. If so, we declare a variable key as KLEP key to hold our key while we modify it. We then check the pool to see if we have any blanks. If so, we take the first key and we remove it from the pool. Done. If not, we need to make a new key, and that's okay, because if we're out of keys in the pool, then we just make more keys. It's like Factorio. We then update the properties of that key and then assign it to the neuron. The update properties function looks intimidating, but all it is doing is copying the data from the KCD to the key itself. So we pass it the key that we just got along with the KCD. Then we assign the name, the attraction, and the key loader that it belongs to. These should all be a part of the KCD. Then we call initialization for the loader to fill in any default properties and values that the key should carry. That's all /keyloader stuff. We then go through all the properties of our KCD and see if the key has that property. If it does, then we set the property value to our KCD value. If it doesn't, then that's where the fun comes in. Currently, we add the property to the key and move on with our life. This does not add or modify the properties of our key loader. It could if we want, but it doesn't. And doing it this way means that the system doesn't break and your key loader remains untouched by possibly unwanted information. Let's say you are pushing a key for a frame that needs to carry a bool for some reason, and this is outside of the data that's usually governed by the key loader. This then lets you add that for a frame with the bool without polluting the properties of the key loader, as key loaders are scriptable objects. So any changes you make during runtime will persist once you hit stop. So obviously, since that data persists, it can lead to unwanted results and cleanup. What's that, Ross? What if we have a KCD that doesn't have a key loader attached to it? Well, we do have another function that we'll discuss in a little bit that can find a key loader for you out of all possible key loaders that it knows about. Now, if that should fail as well, we have workarounds. But we'll get to that in a second, and I don't want to confuse you because this is already confusing me. And so that is it for pushing to the neuron. That's done now, right? So we've updated the properties, we've pushed to the neuron. Now pushing to the buffer is nearly identical. First, we make sure that we have a KCD being passed to it, and then we call our issue or update key to buffer. And first, we check if a key already exists in the buffer. If it does, then we skip everything and just update the key's information from the KCD. If not, then we go through the exact same process outlined in pushing to the neuron. We kind of did this backwards, but let's go and take a look at the initialization function. Here we load all of our key loaders, and this can be changed and will be changed down the line. We're doing it this way because I'm lazy, and /keyloader is very new to the system as of recording this, so things will change down the road. The goal is to be able to make keyloaders independently from department to department, compartmentalizing their development and allowing it to be brought together here in the key manager. So department A can be working with a KLEP system, and they can be using this key loader, and department B can be working with the same system, right, KLEP system, and use a different key loader. And then when they bring their stuff together, then the key manager, it just has to say, oh, you got this loader, oh, you got this loader, oh, okay, cool, and then it will work out of the box regardless of what you're pushing. The next part is loading up the neuron with all the initialization keys. So these are normally keys that are immune to the key life cycle, but they don't have to be. They can be like primary mover keys that get the chain of influences rolling. This mainly is checking for the make unique flag, and if that's been checked. If it has, then this calls the clone function, which creates a deep copy of the key. If a key is a shallow copy, then any modifications that happen to that key occur across the system. So let's say you have a key that's a health pool, and you're using a shallow copy. Then every creature that uses that key will have that health pool. Unlike a deep copy, where every creature will have its own unique, unshared health pool. So, shallow copy, you kill one goblin, you kill all the goblins. A deep copy, you kill one goblin, you still have to deal with the rest of the goblins. Alright? Finally, we have three supporting functions. Find key loader, which looks through all the key loaders, tries to find the best fit for the list of properties that you send it. This way you can check if a key loader is present in the system that can support or is a better fit for a key that you are creating dynamically. If none is found, then it can return the one that allows for foreign keys, if you have one. And this is where you can dynamically add the key and its properties to that loader. Right? So I'm kind of thinking that in this weird topsy crazy world, we have key loaders that are intelligently designed by us designers, and then we have like the garbage bin key loader that we just set to be dirty, and anything that you push to it, or anything that you push to the system that isn't a good fit, it's just going to go into the garbage key loader, and that'll just store all of those properties. What's nice about that is you can then look at your system down the road and say, oh, okay, well, these aren't really tied up and these aren't very clean. We should probably go and look at those keys and what's pushing those keys and better develop that system. We then have copy key and trade key. Both are super simple. You just pass it the target neuron and the source neuron, which is usually itself, and the name of the key. If the key exists, then it pushes a copy of that key to the target neuron, or it removes the key from itself and then pushes the key on over. These aren't very well developed, but they're very simple to develop. This is another reason why KLEP is so cool. AI communication is seamless, super easy. This can be improved very easily by, like, say, writing a function that updates information if the other neuron has a key present, for example. So an example of that is when I was first making the system, I was doing a AI agent that would put out fires, and it could refill its little squirt bottle over at a bucket. Well, the other agents didn't know the location of that bucket, and that bucket can move, but the agents could communicate with a key saying, hey, this is where that location is last time I saw it. Here's the timestamp on that as well. Oh, your timestamp is more current? Okay, I'll update my information. You see how that works, how seamless that is? Because it's all just keys, you know? So anyways, that's it. That concludes our dive into the key manager. And this concludes our talk about keys in general. And I'm so thrilled about that because I'm really getting sick of just talking about keys. I want to get to talking about executables, and those are really cool. Those are the exciting things. Executables allow the AI to affect the world around it, move around the world, sense the world, so on. It's the stuff that you think about when you think about AI. Keys, that doesn't sound like AI. Anyways, if you want to reach out to me, you can do so on Twitter. If you want to email me, I already got a scam email from some Indian dude, I think. If not, I apologize. But I'm definitely not going to click on any weird links. And support me on Ko-Fi or not, because that's still not set up. I'm lazy, I'm tired, so I'm going to go and take a nice nap. Thank you very much for your time, and thank you very much for your interest.